Hello. This is the beginning of our lecture on statics and torque, and we're just going to spend one lecture on this. Um, but torque is a pretty crucial problem, and it actually will play a lot into what we do when we talk about rotational motion. So let's get started. We first have to figure out what torque is, right? So we've talked a lot about force, and what we've been talking about is translational motion. So if you look at this diagram up here, you draw a free body diagram of this, and we just have one force in one direction, right? I mean, we'd have weight one in that direction, but for the time being, we'll just have one force in this direction, and we would expect in this x direction that the hockey stick would move, right? But we also have to deal with rotational motion. And so if we look at this image down here and we apply a force here and a force there, if we just dealt with translational motion, we would draw a free body diagram that looked like this. And we'd have two forces that balance each other. And we'd say that stick isn't moving, right? There's no acceleration. But experience tells us that that wouldn't be true, right? If I push this here and I push this there, the hockey stick is going to turn, right? And so that's what torque is. Torque is the application of what's called a force pair, okay? And that one of those forces might just be holding it still. It might just be an axis. That creates a rotational movement of an object, okay? And so torque is essentially a rotational force. It's something that tends to make something accelerate in a turning direction rather than a translational direction. Okay, so how do we calculate what torque is? Well, we can find the magnitude of torque by looking at not only the size of the force, but how far away it is from the axis that's turning. So if we put a nail in our hockey stick right here, and we apply this force, our magnitude of force is going to be determined by this force, and then also by what we call the perpendicular lever arm. Now, what is it perpendicular to? It's perpendicular to the line of force here. So this force is going in this line, and we can draw that as far as we went in either direction. And then we're going to try and find the place where it's perpendicular, a line that's perpendicular to that, that goes through our axis. And there's only one line that does that. Like a line that's perpendicular to the axis here, or to the force here, doesn't actually go through the axis. And we call that our perpendicular lever arm, and we indicate it this way with an R sub perpendicular there. Now, if you think about this, we know just by experience that the best way to use a force to turn something is to push it where this is large, right? And so the equation becomes here, the size of the force times the size of that lever arm equals the torque. So consider opening a door. Where do you push a door to open it? Do you push it right by the hinges? No, you don't push it by the hinges. That requires a lot more force than if you push it next to the handle. And so that we're pushing it next to the handle, we're making our perpendicular large, and that increases the torque, the tendency of that object, the door in this case, to rotate in a rotation, or to accelerate in a rotational direction. So the perpendicular lever arm, if we look at this geometrically, we can figure out the angle between the force line and the line between that point of application and A, and that gives us an R here, right? And then we can use sine of theta to figure out what that R perpendicular is. So if we combine these two things, we get what's the most common equation for force, and that is Fr sine theta. So we take the magnitude of our force in newtons, the length of our R in meters, or whatever length we were dealing with, and multiply it by the sine theta here. So if our R is the same as that perpendicular lever arm, the sine of theta ends up 1, and we just multiply F times R. The symbol for torque is the Greek letter tau, which rhymes with cow. Tau and cow. All right, so let's do a quick problem just to, because getting a good sense of how that lever arm works is can be difficult. So if we apply a force of 10 newtons here, and we have a theta of 60 degrees, and our R is zero point 0.1 meters, we can calculate our force, and we can take a guess here, right? So we know our R is going, our R perpendicular, our lever arm is going to be smaller than this, right? Because it's going to be shorter here than our long R. So we would expect an answer that's going to be under 1. Um, so we do our calculation, tau equals FR sine theta. Throw in our values here, our force, the length R, right? And sine theta, that's that angle there. And we get 0.87 Newton meters. Okay, so we're a little under 1, just like what we expected. Now, notice the units here. They're Newton meters, okay? We've seen that before, right? Energy had and work had the same units, but they're not the same thing, okay? So you have to be careful not to confuse torque and energy. Usually it's pretty easy to keep those things clear, but this is why oftentimes we use joule for work and energy rather than Newton meter. Newton meter is sort of reserved for torque. All right, we could also calculate this just to get a sense of what that lever arm means. We could calculate this and find our lever arm, right? Draw our triangle, find our perpendicular, and we could calculate that out. We'd find that it's a little under 10 centimeters. And then we could use this equation for torque now that we know our perpendicular, and we would get the same answer. Okay, we've essentially done the same thing, right? We're just multiplying R times sine theta times force, and so we get the same answer. But there are a lot of problems where if you look at the problem, you can actually figure out what R perpendicular is without going through using the theta. So just think about where that line is and see if you have a measurement that's going to give you the distance between that force line and the axis, and you can actually save yourself a little trouble. Now, the last thing to say about calculating torque is you always have to say where the torque is around, okay? Because it's going to be different. If I put my nail here, my torque would make the hockey stick turn in that direction, right? So I'd have a different torque around a different axis. So you always have to think about what your axis is. So when we write the answer to this, we would write something like this. 0.87 Newton meters counterclockwise around point A, because the tendency is for it to turn in a counterclockwise direction. So always include that as part of an answer when you talk about